Hello, my name is Shamin Shumi, and this is our project on breast cancer prognosis using machine learning to predict patient survival from cancer registry data. Our goal was to predict cancer survival using machine learning on sheer cancer registry. We compared three models: a neural network, exibos, and random survival forest. We built a neural network with TensorFlow and Keras. It had an input layer of 128 neurons and a hidden layer of 64 neurons, and used ReLU and sigmoid activation. We trained over 5 approaches with the ADAM optimizer. The neural network achieves 87.93% validation accuracy with a validation loss of 0.32. It identified about 55,000 alive and 11,200 dead patients with an F1 score of 0.92 for alive and 0.71 for death. We use XGBoost classifier with 300 estimators and random state 42. We also visualize the tree to improve model interoperability. XGBoost achieved 92.29% accuracy. It defined over 54,000 alive and 15,000 dead patients with strong precision and F1 score of 0.95 for alive and 0.85 for dead. For random survival forest, we used 5 trees and analyzed feature importance. The top predictor was the number of positive lymph nodes. The survival curve shows a clear separation between high risk and low risk groups with a concordance index of 0.85. Comparing all models, XGBoost had the highest accuracy and fastest training time, followed by the neural network, while Random Forest had lower recall but still performed well. Finally, we implemented XGBoost Cox for survival analysis. Kaplan-Meier curve showed clear survival difference across risk group with a mean AOC of 0.785, indicating solid predictive performance. So for the live demo, here we imported TensorFlow and set random seed to make sure the results are reproducible. This is the model architecture code. It shows the input layer with 128 neurons, dropout to reduce overfitting, and two dense layers with ReLU before the sigmoid output. We trained for 5 approaches. You can see from the log that accuracy improved each approach, and the validation loss keep dropping. So we knew it was learning. Down here, the plot of accuracy, the loss curves, you can see validation stabilized nicely. And here, the confusion matrix output, you can see visually how many alive and dead predictions we got. And here's the precision recall curve, achieving a PRAUC of 0.8150. For XGBoost, we use 300 estimators, and this line here shows the classifier setup. We also visualize one of the decision tree like this. It's a bit small, but it helps check which feature the model was splitting on. After fitting, we evaluated with the confusion matrix again. Looks pretty similar to earlier, but with slightly higher death cases predicted. And here, the precision recall curve, it achieved a really strong AUC here, 0.9139. Now for survival analysis, we use SkyKit Survival's random survival forest. We one hot encoded the data handled missing values, and and um, this is where we trained the RSF model. Finally, here's XGBoost Cox for survival analysis. We use the survival Cox objective. We split patient into low, medium, high risk using predictive risk score, then plotted the Kaplan-Meier curves. There's a clear separation here. The low risk group maintains better survival over time, And here, the time dependent AUC curve around 0.785, showing stable predictive power across